Should be good now.
Good morning, everyone. I'm Weijia Xu. I'm the research director for the Good Systems Smart Cities, and also the group manager for the Scalable Computational Intelligence Group at TAG. Good System is a UT Grand Challenge with mission to developing human AI partnerships that can benefit society. Smart city technology have great potential to contribute to these missions. To advance our knowledge and the research around smart cities, we have started this lighting presentation series every Tuesday from 10 to 10:30. So for today, we are delighted to have the work from Dr. Sean Qian. Dr. Qian is an associate professor, jointly appointed in the Department of Civil and Environmental Engineering and Information Systems and Public Policy at Carnegie Mellon universities. So without further ado, I will turn the floor to Dr. Qian for his talk today. Dr. Qian, please go ahead.
Thank you, Weijia. Really appreciate this opportunity to be virtually here. I know pandemic has really kind of prevented us to travel, and honestly, I have never been Austin before. Although I give a couple of talks on online forums and everything, but hopefully that we'll have opportunities to discuss more research in the in person in the future. So today I want to by the way, I really appreciate the format of having lightning talks, and I'll be very brief, and I just want to convey a couple of research ideas that we have been recently working on, and we can have more discussions afterward and taking questions and take your suggestions. This is a very preliminary study we did recently. First of all, I want to give full credit to my PhD student, Rick Graham, that he did most of the programming and a lot of analysis. And this research is fully supported through the University Transportation Center the CMU has with the USDOT. Right? Really, the ideas about the first and last mile services, I want to start just by give a little bit of intro of why this is so important in Pittsburgh. And I suspect this is also very critical for many of other cities in the US as well. The idea is that a lot of cities it was informed in a way that there's a highly densely populated area in the center of the city, and then there are people in the suburban rural area traveling to the center of the city to access a lot of resources such as opportunity, employment, food, and healthcare services. Right, taking commuting as an example in Pittsburgh, there are many different parts of the Pittsburgh in suburban rural areas going to the city, or maybe going from the city that going to other outside places. But the public transportation, a lot of people are captive to public transportation systems. So these public transportation systems are very expensive to run in the US. And on the other hand, they they only comes at every 20, 30 minutes during the commuting hours. They can only cover very limited areas. The catchment area is very limited. So the idea was really here to, hey, about all the entire rural suburb population. If the transportation system can not really cover their entire trip from the origin and all the way to that destination, where it's really their critical resources, can we fill this gap by providing first and last mile services, where the service allow them to take some kind of shuttle or some sort of a way of public transportation, but it's kind of very agile, very on-demand services, get them to the public transportation main lines, where the public transportation main lines can take them to the resources. So that is the essential idea. And in order to, with this idea, I mean, there are some studies in the US already, some, not that many though, in some theoretical research. There are also some pilot studies, but what we want to do here is that we really want to do answer a couple of using this pilot study in Pittsburgh, where you can see here that this is the area that the pilot study, the first mile service, has been going on for since 2009. And you can see these red dots are some are big, some are small, but these are the employers. I just give you some example. This is part of the Pittsburgh Airport corridor. The highway goes directly to the airport, Pittsburgh. And this is a kind of booming area where a lot of small businesses, and including some of the big ones, the FedEx, Marriott, hotel. So these are provide a lot of job opportunities to people. But the issue here is this is a suburb area. How do we get people from the center of the city, maybe other parts of Pittsburgh, to this part of job opportunities, right? So just to give you a little bit of background, this P right here, this is IKEA furniture store, and this is where the mainline bus comes every 30 minutes or so and make a stop, and it goes directly. Next stop is really the airport. So you can imagine that without this first mile services, it's really a challenge for people to get access to these jobs. So here, what we do is we want to evaluate the data that has been collected over the last 10 years to really take a closer look at how people make trips, and whether we want to evaluate how to improve such a first mile, last mile services to create a general platform to be able to provide this first mile, last mile services most effectively. Therefore, we can improve the overall transportation system, multimodal transportation system efficiency, so which allow people to have access to employment and healthcare more easily, right? So a little bit background again, this is roughly covers about 200, this whole little area, that's roughly about 6 square miles, covering about 250 local businesses. Like I said, some of the big ones, the call center, FedEx, these are the big employers, but some are very small, tiny. There are a lot of big box stores, and people travel to there just to work. But the service right now runs from 6 to midnight during weekdays, and it's right now it's 2 25-seat shuttle services with online boarding, with onboard Wi-Fi's. And right now they use an app users can do 2 things. One is online, kind of on demand. They can call for service anytime they like, or they can walk up. It's what they call walking without really making any reservations. So essentially 80% of the time people walk up, they do not really do any reservation because again, for a group of population that use this service, the technology they have access to is also pretty limited. That's another thing that we have to consider when we design the service, right? So at the overarching idea, again, I'm going to skip everything about the development and all the theory side, but I just want to sort of look at what we do with the overarching question and directly go to the last few pages just to tell you a little bit of sort of what we find out through main findings through this research. So overarching idea is the demand side. There are jobs, but it's very sparse. It's not as dense as the central area. We do have the real data, right? On the supply side, we have the bus line that we know as a fact that they comes every 30 minutes, and they only make a stop somewhere in the middle, and we know the roads, the topology of the network is in this little tiny area, and we also know TNC existed right there. People are able to call TNCs, but it's very expensive. It's almost like $10 within this area per trip on average. And then the objective is that for agencies to run such a service, they want to consider mainly 3 things where they can make a trade-off among, right? And first of all, about the user cost. The user cost is about, here where we discuss the user in-vehicle waiting time and the waiting time for the shuttle services, as well as the waiting time for buses. So these are what we consider as a part of the user experience. We want to minimize this cost as much as we can. And number 2 is the agency cost, right? So in order to run the service, technically you can call TNC anytime for any user, but it's way, you can see it's actually not so bad depending on the demand level. But again, if there's a lot of demand, the cost can boom tremendously. So we want to also minimize the agency cost as much as we can as well. Number three, which is very critical for those opportunity employment, oftentimes we omitted this as well, is the reliability. So in a way that these people, any commuter actually, if they go to work, so they need to get there by a certain amount of time, right? Otherwise they're risking losing their job, being late. So reliability defined here in this case is 95 or 99 percentile of travel time has to guarantee people to get there by within X amount of minutes. So, and again, these are the kind of the goals what we try to provide the first mile services for. And in the way we design the first mile service is two things. One is at the high level, at the strategic planning level. So we want to determine, hey, how many shuttles, what's the shuttle size, how many shuttles we need. Right now we use 2, but we know this is not optimal, right? Number 2 is that shall we allow people to, shall we provide fixed route services, or this has to be on-demand service? And stop aggregation is that you can see this is a wide spread area, and sometimes the employers could be very, very close by. Shall we allow people just to can aggregate the demand at the stop level and asking them to walk a little bit further just to gather these demands so that the bus can go there just to pick up and drop off more effectively? And again, the last one is really how can we coordinate the first and last mile services, buses, and the TNCs? Because sometimes, for a bus, which is or shuttle service, which is very far away, in response to the on-demand request, that may take the shuttle another 10 minutes something to get around. You might be better off just to call a TNC service occasionally just to feed this to fulfill this requirement or this request, which will save. It's really can be better off for the entire system. So how do we coordinate the bus service, shuttle service, and TNC? Really, it's a real challenge, right? So this is strategic design, but operationally, we want to develop an optimal kind of real-time vehicle routing algorithm and the demand matching algorithm together simultaneously. So therefore, we can provide a fast turn-by-turn navigation to the drivers for pickup and drop-off. Also provide the best service experience for users. So these are the kind of things that we do. I'm skipping some of the details, but I just want to show you kind of very briefly what we found out. So in this Robinson Township, which is the pilot study has been going on for 10 years, what we first do is we create a real-time operational model. The idea is very simple. We try to do real-time optimal vehicle routing and demand matching using because this is such a big system. You can see the request right now is roughly about 150 to 200 requests per day. Using kind of very theoretical operations research model, optimization model, it's not so tractable in many cases. So where we develop some sort of what we call insertion heuristics, which are able to address this problem in a pretty sizable real world network. Right? I'm not getting into details, but the essential idea is that every time a new request that comes in, we sort of look at the marginal cost of adding this additional request in any of the positions in the current pickup drop-off queue for each shuttle. And we look at the marginal cost, and we not only will look at the marginal cost for each shuttle, but we'll also look at comparing this marginal cost to a cost of serving this particular request directly with the TNC service, Uber service. And we have the pricing model for Uber. But the idea here is that, hey, look, if we have $10 Uber that can serve this directly this demand with 5 minutes waiting time, which we estimate the average waiting time of calling for Uber service in this area is 5 minutes. And why don't we just turn the Uber to serve this particular person, right? Instead of asking the shuttle to turn around to pick up. So that is really the essential idea. Therefore, we define this ratio of lambda right here, which is the marginal cost ratio. The bigger lambda is, then that means that we're gonna ask less TNC calls. In extreme cases, if lambda is infinity, means that we only using shuttle services. If the lambda is very little, right, means that we're more likely relying on the TNC services rather than shuttle services. And then therefore we can optimize the lambda, we can optimize the entire services using this parameter, right? It's really, again, about integrating the shuttle services with the TNC services, because both has the pros and cons. We want to fully integrate the two services to see when is really a good, the sweet spot to provide integrated service and how. A couple other technical details. I'm not getting details, but I think that really the key point, the takeaway message here is that when we design the algorithm, we do consider the equity concerns. We're making sure that no one's waiting time is waiting time or in vehicle time is more than 30 minutes. Okay. We also emphasize a lot about the reliability measures as well. So another thing we discussed in this study is that we actually look at the time at the transfer stops, because these are where people wait at the mainline bus stops to wait to be picked up or drop off by the mainline buses, right? Because we also want to make sure the transfer is seamless. So therefore, we also, the part of the user cost also include that time, waiting time at the transfer stop. Another thing we discussed, I mean, there's a lot of practical issues when we discuss with the agency, try to optimize the services. Another one was trying to do predictive analytics. So we are able to predict ahead of time, 30 minutes ahead, for example, how many demands are going to show up in what specific, for each specific employer, particularly those big ones. And we're able to position or allocate these bus service, the shuttle services much more effectively, spatially and temporally. Okay, and so here's the very first slide of the results. I think I'm a little over time, but I want to wrap up very quickly. So first, what we do is that we say, look, we're not going to use any TNC for now. We're just going to deploy our algorithm just to see, comparing what's happening right now, the service performance, and we're going to apply our new kind of routing and matching algorithm, right? And let's see how much in efficiency we can improve, assuming that we have the same traffic condition, network traffic condition, and we also have the same exact demand request, because we have the data about what time people request where to be picked up or where to drop off, and we know this demand. Assuming this demand is the same, we just apply the new routing algorithm to see how much benefit we can get. So this is pretty promising. We can see that using this new algorithm, we're able to reduce 21% of the waiting time and 30% in-vehicle travel time, right? So the other thing, and we want to take a look is, what if we incorporate some of the TNC services into this? Are we able, right now, and they use the 2 shuttle services, and then are we able to effectively reduce the number of shuttle services while still improving the entire system performance for both users and agencies? So the answer is very, very exciting. I think the answer is yes. So if you take a look at this point, right? So this is the green line, shows that if we set the lambda being 1.8, this is about the time break even, meaning that for the agency, the cost of providing 2 shuttle services is the same as 1 shuttle service plus whenever people request over TNC, and not the people request, but whenever people request a ride, with this lambda, we are able to send some of the requests with the TNC service. This is the break-even point. The cost of running the service is the same. Oh, by the way, I forgot to mention, right now the pricing model for the shuttle is $51 per hour to rent 1 shuttle with the driver included. So that is the Pittsburgh kind of pricing. And you can see, in fact, if that's a break-even point, you can effectively reduce, right, the user cost or user waiting time with 1 shuttle and some TNC services comparing to the 2 shuttle services. Okay, and then this is pretty reliable, and then we can actually later on, I have the slides, and some of the slides are later on, I probably don't have time to discuss today, but we show that in some other areas in Pittsburgh, we did some same analysis. We can show that with the proper setting of the lambda, you can see that one shuttle service plus TNC is actually better than two shuttle services in terms of it's more flexible. It reduces the agency cost, and it also improves the services comparing to two shuttles scenario. Okay. The overall into our conclusion is that integrating TNC is optimal, and we can also see that in the morning peak, where the most of the services are last mile, meaning that people go to work, right? And then during the day, then some of the people do shopping, some of the people do healthcare services. It's a mix of first mile and the last mile trips. Then you can see one shuttle service plus TNC is better, but for morning peak, the two shuttle services is better. It really changes over time depending on the trip purposes. You can see with the TNC, you can also improve tremendously the 95th percentile of the travel time, which measures the reliability as well. So there are a couple. I don't think I want to discuss more. I do want to leave a little bit of time for discussion. But overall, we have been discussing very practically with the agency how to improve the service by doing predictive routing, by doing transit bus service coordination. Overall, we're able to effectively reduce the waiting time, improve the system performance. So these are all the very good theory and the very good kind of lessons we learned from this study, and we're trying to implement it to a couple other places where there's no current service, but we try to estimate the demand. We use this platform to evaluate, hey, based on what type of service are we providing, how much of the total system cost is we anticipate to see, and how do we optimize the model to run the service. And I think I'm gonna have to stop here. And by the way, this is we have a report online, and what we find is that if you have more demand, medium to high demand, right? Usually having a combination of shuttle service and the TNC is actually a better choice in terms of user cost and agency cost. Okay, so I think that's what I want to talk about today. And I would appreciate any questions or any suggestions, advice.
Thank you very much. It's a very interesting talk. I can start with one question. Is so in your optimization, do you also considering like a historical record or people's travel patterns and trying to optimize it, or are you planning to incorporate those?
Yes. So let me see if I have the slides over here. So there are two things that we incorporate the data for this particular area that the service has been going on for 10 years. One aspect is we utilize the observed time varying travel time in 15 minutes interval, because because this is a small area, right? What nice thing about the first line of service is a small area, and the point of interest is, like I said, is roughly about a little over 200 employers. And we're able to enumerate all the possible connections based on historical data. People travel from A to B. We can measure their travel time really among any pair of origin destinations within this little area. And because we have many years of data, we can use the time varying travel time, incorporate that time varying travel time in our optimization, the routing and the demand matching model, and without really necessarily have to predict ahead of time what the travel time might look like in next 15, 20, 30 minutes or so. And because the possibility of having enumeration, so we don't have to run the shortest path or whatever the heuristics in real time. So that really helps with the real time data. So the actual data, not real-time data. But the other thing is we did was that the model can incorporate any sort of demand request in real time. But we do hope that the predictive routing means that if we know based on historical data, this is actually exactly what you meant, was that because we have historical data, we know maybe 7:30, that's very likely this FedEx big box store, big box warehouse has some requests that people want to travel go, right? So with the historical data, we can build in this predictive model that tells us, again, 1 hour ahead or 30 minutes ahead what the demand is. And that's based on historical data and also based on the real-time data. And maybe today's pattern is that more people are likely to travel, but we'll also incorporate some kind of weather condition as well. That's something you can use historical data to learn. And once you kind of be able to predict the real-time demand, 30 minutes ahead demand, then we can incorporate that information into routing to enable better efficient routing services.
Okay, thanks. That's very interesting. Is there any question from the audience?
I have one question. My question is that in your modeling, does the demand exceed the shuttle capacity or not?
That's a great question. So we could, but in this particular study, we do not. The reason is, as you can see in this Robert, most of the first last mile services, right? And you can see here, well, at least in Pittsburgh, speaking to only to my experience, you have roughly about 150 to 200 trips per day, and in peak hours, you're probably looking at 30 to 40 trips requests per hour, some areas. And even with one shuttle, we almost never reach the 25 seat, I think it's 23 or 25 seat capacity. And if you use a small van, I mean, we did, when we did a simulation and the routing everything, we did check the maximum, so the number of passengers required for these services. Well, we observed there was never a time that exceeds 9 passengers. I think 8 or 9 is almost like the top, and then it only happens once a month or something. So right now, the seating capacity is not really of a concern in this particular study. And then this is actually the area, based on my discussion with a lot of stakeholders, this is the area I think the demand is already exceeding, at least a pre-COVID, not right now, but the demand is already pretty high. And the Moon Township, the other township that we're right now doing some demand estimation and service design, that's roughly about 40 to 60 requests per day. So therefore, we do not think that for most of the first mile services, the seating capacity is a really big concern at this point.
Thank you.
So if there's no more questions, and I want to thank Dr. Qian for spending time and give us presentation of this very interesting talk. So if it's okay with you, we will post a recording through our website.
Yeah, I signed the release form yesterday, so feel free.
Okay, thank you very much. I also paste our link for our Smart City website there, and we have another talk coming up on next week on Tuesday, and hopefully we can see everybody there as well. Thank you everyone for attending, and thanks again for Dr. Qian to give us these wonderful talks today. Bye everyone.
See you. Bye.